Do this, please. You'll find this easily on the website. Final official time, 3 to 5 p.m. But if you can get here by 2:45, I'll give you 2.5 hours. I think you'll be happy with that. 26 questions instead of 24. And as soon as I get the final composed, I'll provide some specific hints, directives as to which past exams and quizzes to take a look at. And regarding past exams and quizzes, I'll tell you which questions to look at to relate to the stuff which you're going to expect to see on the final. Because we've done a lot of stuff. And I don't think it's reasonable just to say everything is fair game. But do keep in mind, if you turn in a particularly strong performance on the final, I'll take that into consideration regarding determination of your letter grade. Information on this is in the syllabus. The review, which I asked for, the registrar tells me this room is unavailable. I don't know why, but we'll survive. We've been given Lee 207, which is the second floor of Lee, a comfortable place, so we'll do fine there. So be there this Friday, period 5, and we'll move on into period 6 as necessary. Regarding review, it will be my intention to entertain questions to get at review considerations, questions presented by you which come from past exams. So I'll bring a collection of past exams, all the exams for this term, plus final exams for the last 4 terms, something like that. And all you need to do if you wish to ask about anything regarding these questions from the past exams is to tell me which question and which exam. And if I can't answer it, then we'll put that one on the final for sure. How's that?
Do you know about when your exam will be written?
If I had that good a crystal ball, I'd be in the business of predicting lottery numbers. No. Soon as possible. I'm working on it now. I'll continue working on it today. With good fortune, I'll have it done tomorrow. Now then, we will now focus on stereoisomeric properties of transition metal complexes and limit our considerations to octahedral complexes because they are the most common geometries shown by transition metal complexes. An octahedron. Octa, 8. Because this thing has 1, 2, 3, 4, 5, 6, 7, 8 faces. Each of which for a perfect octahedron is a perfect equilateral triangle. And 6 coordination sites. 1 at each corner of the octahedron. The complex metal atom or ion, of course, is in the dead center of the model. As represented by a ball and stick model where this is the metal atom or ion. You've seen these models before. Stuff you talked about yesterday which introduces you to this consideration. Geometric isomers. Notice that the composition of this stuff and the composition of this stuff identical. But they're not the same. Because the geometric positions occupied by the ligands in the coordination sphere, the ligands which are coordinated to the metal, which I have excluded from the sketch for simplifying the sketch, the geometric positions are different. For this, the B ligands, of which there are 2, are at a 180-degree angle with respect to each other. Whereas for this, the B ligands, again of which there are 2, are at a 90-degree angle with respect to each other. So the language we programmed you with yesterday is trans for opposite or across from, cis for being as close as possible to each other. And by now you should have recognized that even though an octahedron has 6 coordination positions, geometrically it's a pretty simple object. There's only 2 bond angles of consequence. 180 degrees, corresponding to trans orientation of like ligands, and 90 degrees, corresponding to cis orientation of like ligands. That's it. This is a simpler geometry than 5-coordinate trigonal bipyramidal. How can you recognize that? 5 coordinates got 3 principal bond angles rather than 2. You've looked at this before. For trigonal bipyramidal, 180 degrees, 90 degrees, and for the 3 atoms in the equatorial plane, 120 degrees. But we're not going to do any of those because we just don't have enough time. So with cis-trans language, we can distinguish between, from a nomenclature standpoint, these 2 geometric isomers. Now then, what if in this first coordination sphere we have 2 sets of ligands, 3 A's and 3 B's? If all the B's are at a 90-degree angle with respect to each other, and all the A's are at a 90-degree angle with respect to each other, then all the like ligands are cis to each other. So probably you could get away with calling this all cis. But the preferred language is to use facial, which means like ligands are in the same face. One here, one here, one here. Or one here, one here, one here. Doesn't matter as long as the like ligands are all on the same face. Facial. I can show you that with the ball and stick model as well. Here, these 3 red ligands are all on the same face. As opposed to this possible geometric orientation of the 2 sets of like ligands. These A's are trans, but these A's are cis, as are these A's. These B's are trans, but these B's, as these B's, are each cis. So now the cis-trans nomenclature is going to cause a problem. So instead, we opt for the language meridional. Because for this geometric orientation of like ligands, we can recognize that a perfect octahedron is inscribable in a sphere. You can wrap this up with a sphere. Or you can imagine this being wrapped up by the surface of the earth, which is rather like a perfect sphere. And you know that the map makers, the cartographers, refer to circles that go around the surface of the earth as meridians. And a meridian with which I'm sure we're all familiar is the equator. So if we use that kind of language to name this thing, recognizing that if I have an A ligand here and an A ligand here and the remaining A ligand here, they're all on this circle, this meridian, which wraps around this octahedron. As would the B be the B ligands, one here, and one here. They'd be on a circle, an equator if you wish, that wraps around the octahedron in this direction. So for this geometry, we'll call it meridional. You'll see this stuff illustrated again if you take a look at these videos. Now then, let's proceed to some additional considerations. besides geometric isomeric behavior, another very important stereochemical behavior shown by many transition metal complexes and many materials which are not necessarily transition metal complexes, like your left hand and your right hand, is that of optical isomerism, mirror image isomerism. I expect that you've all had the experience of observing a left hand shown to a mirror. What do you see looking back at you? A right hand. You show the right hand to a mirror, what do you see looking back at you? A left hand. Now then, all material objects which are non-transparent have a mirror image. The question is the mirror image the same as the object whose image was cast? Or is the mirror image different? If the mirror image is different, the stuff whose object was which had its image cast into the mirror is said to be optically active, because the image is not the same thing. How do I find out? I take the image and lay it upon the object whose image was cast to see if these images are superimposable. Left hand. Let's lay it this way. My right hand. I'll lay it on top of the left hand, and immediately we see the positions of the little fingers and thumbs are obviously different, which tells me these are different objects, optically speaking. Geometrically speaking, they're the same, but optically speaking, they're different. We play the same game with complexes or any molecule to find out if it's optically active. This is an important property of molecules. Are you familiar with the stuff called cellulose? Wood fiber? How about sugar? Interesting. Sugar, for example. We eat, we get nutritional energy. Termites eat sugar, they get nothing from that. We eat wood, we get nothing from that. Termites eat wood, they get nutritional energy from that while our house falls down. Yet, the mirror image of cellulose is a sugar. Consequently, the mirror image of that particular sugar molecule, because there's a whole lot of sugars, is cellulose. Interesting. But one of the images provides us with nutritional energy. The other image provides nutritional energy to our arch enemy, the termite. So with that, let's take a look at this complex. To be able to get at this in a more direct fashion with models, I'm going to call this, instead of diamino, diaquo, dichloro, and please, when you see this in a complex, that's not a coordinated chlorine molecule. That's two chloride ions. It's not this. It is this, which allows you to recognize for this complex. What's the oxidation state of cobalt? What's the oxidation state of cobalt in this complex if the charge on the complex is 0? What is this? +2. Because these are molecules, no charge. These are molecules, no charge. If you were to go away from 2 semesters of chemistry class and not recognize the water thing is a molecule with no charge, I wouldn't know what to say. And chloride ions are each -1. So if the charge on the whole thing is 0, cobalt must be +2. Because I have green, red, and white ligand representatives with the models, I'll call this G2R2W2. G2R2W2. Now I've drawn 2 obviously different from a geometric standpoint, isomers, for this complex, where all the like ligands are trans, versus the opposite extreme, all like ligands are cis. With this, we're going to take a look at this note. If a geometric isomer is optically active, that means its mirror image is something different. It's not superimposable on the original complex's image. If a geometric isomer is optically active, it will be the one which is of lowest symmetry. What's this mean? A simple symmetry consideration. CO2 molecule. Is that a symmetric molecule? My head is a carbon atom. Oxygen atom. Oxygen atom. Double bond. Double bond. Strong, huh? Double bond. Am I a symmetric molecule? What if I'm a water molecule? Oxygen, hydrogen, hydrogen. Now I have a bond angle of about 105 degrees. Whereas for CO2, I'm linear. I have a 180 degree bond angle. Water, CO2. Which molecule has the higher symmetry, is more symmetric? CO2. What if I'm a different molecule from water and my bond angles are like this? My bond angle is this, 90 degrees. How is my symmetry compared to water? Is it less symmetric or more symmetric than water? Less symmetric. What if the bond angle becomes this, 45 degrees? Now even less symmetric. You can look at it this way. Imagine the carbon atom is a rock, and the oxygen atom is an ox. Oxygen ox. Okay? The farmer who owns the ox ends, we'll just leave it as ox. Okay? Ties a rope around the neck of each ox, and then another rope around the carbon rock, because the farmer wants to move the rock out of his field. But he doesn't know anything about physics. If he has the oxes, the oxygen oxes, pulling one this way and one that way, because oxygens are more electronegative than the carbon rock, is the rock going to move? No. This is the way I get at polarity in my 2045 class. If by this game we can recognize the rock doesn't move, then we're looking at a symmetric species. So symmetric that in this case, the resulting molecule would have a net zero dipole moment, would be nonpolar, and the rock does not move. But if I create an angle for the peripheral atoms, which is anything than 180 degrees, like SO2 molecule, you familiar with SO2? The sulfur central atom is 120, is sp2 hybridized, and the bond angle is on the order of 120 degrees. Now does the rock move? Mm-hmm. Which way does the rock move? This way. Because the oxygens are more electronegative than sulfur. A simple way to play the game. So would you accept my contention that clearly between these two, this one is of lowest symmetry? This one is much lower symmetry than this. Because here, if every one of these bonds of the coordinated metal with the white ligands, red ligands, and green ligands, if every one of these bonds is polar, the rock still isn't going to move. But here, you betcha. Might not move much, because there might not be that much difference in polarity for the various ligand metal bonds. But some movement, definitely polar. Now then, how do we get at this optical activity property when we are limited to drawing pictures on a piece of paper? We have to be clever. And one of the reasons why I put this on bonus quiz 3 is to start you at this business of drawing pictures. The rules of the road for drawing these pictures are in the notes. And I want you to follow these rules of the road. I want you to draw canted squares, which means this square is perpendicular to the drawing surface. The canted square for this model is the square containing this white ligand, this red ligand, this green ligand, and this green ligand. They're in this square plane. And this portion of this square plane, if this is the drawing surface or chalkboard, this portion of this molecule is projected toward you, and this portion of the molecule is projected away from you with respect to the drawing surface. So take note. If I take this molecule and show it to a mirror, what image will I see in the mirror? These ligands are closest to the mirror. These ligands are in the plane of our drawing surface, and these ligands are furthest from the mirror. So immediately I can do this. Because those are in the drawing surface. I'm talking about ligand up here, ligand down here, which you might recall can be identified as being axially oriented if I hold a model like this. All right? What's over here? G green. Over here, R red. Over here, W white. And here again, W white. Now comes the $64 question. Are these the same things? Or are they different? Let's take a look at our models. Compositionally, at a glance, I'm sure you can see the models are identical, except for the fact that I ran out of gray parts, black parts. So never mind the central atom. Okay?
The charcoal is almost black.
Almost. 2 cis reds for each, 2 cis whites for each, 2 cis greens for each. Well, let's hold this one like this. Here's my mirror. The reds are closest to the mirror, so I'll hold this one like this. The reds are closest to the mirror. Here's the mirror. Green up top, green up top. White down below, white down below. And green over there, white over there. Green over there, white over. These are not mirror images, are they? What do you think they are, if they're not mirror images? Well, let's first make the mirror images and then we'll repeat that question. What I'm going to do is to break this bond and break this bond, I hope, and remake this bond over here. And remake this bond over here. And go back to the models. Do you agree that these are now mirror images of each other?
Yes.
Wonderful. There's the 2 reds, green up top, white below, and back behind the drawing surface, green, green, and out in front of the drawing surface and closer to you, the whites. The test to find out if they're the same is that of superimposability. So, I'll lay the reds over each other. And notice here we have matching greens and here we have matching whites. But look what we have here. Green, white, green, white. These are different. So what are we seeing? We're seeing that for an octahedral complex of this composition and geometry, the mirror images are different from each other, optically active. It has a mirror image which is truly different. Now, do you remember what I did to make this the mirror image of this? I broke and remade two bonds while maintaining cis geometry. And the bonds which I broke involved different ligands. Now, before I played with these two, all right? Let's see if I can pick a different pair. Let's break this bond and this bond. And then remake as I've shown you. Still all cis. Reds, green up top, white below, but look what we have here. Are these mirror images? No. Are they the same?
Yes.
Yep. Let's find out. How about that? Two reds, two greens, two whites, two greens, two reds, two whites. They're the same. So in order to go for a complex like this, optically active to non-optically active, break any two bonds involving different ligands, remake while maintaining cis geometry, and you will turn optically active into the same, or vice versa, same into optically active. Now, the task that you have is, how do I play this on a piece of paper? Well, let's take a look. Here's this, which we see to be the mirror image of this, and which we now know to be different from this. How can I demonstrate this on a piece of paper? All right, here's how. I'm going to take this, let's get this out of the way so we can sketch upon it. And I'm going to hold this by the top ligand and the bottom ligand, just like this. Okay? And I'm going to rotate this thing 180 degrees. When I rotate this 180 degrees, this is my axis of rotation. This thing is going to come over here. This is going to come over here. This is going to come over here. And this is going to go over there. Just like that. All right? Now let's do it on the board. Since I rotated by using the top green with the central metal and the bottom red as my axis of rotation, their geometric positions remain the same. Where'd this wind up? Over here. Green. Where'd this wind up? Over here. Where'd this wind up? Over here. And of course, by default, you recognize the remaining position is occupied by red, which of course corresponds to this red moving over here. All right? Now let's look and see what we have. Here's the object whose image was cast. Here's its mirror image. We've proven with the models that this mirror image is not superimposable on this. These are different. So, take a look at what we have obtained by taking this picture and not changing it, just rotating it in space, like the wind blowing it around. G up top, R down below. White over here, right over here. But look what we have here. GRRG. And that's how you can prove this on a piece of paper. You got plenty of time to practice from now till next Monday. Now, we've taken a look at this. Let's go to this question. Here's this same stuff. We're going to consider taking this same stuff and treating it with ethylene diamine. Now then, if we go back to the original, we can ask the question, which most of you wrestled with yesterday in discussion class. Here again is ethylene diamine. These are bonds to hydrogen. There's a water molecule ligand. Chloride ion ligand. And of course, ammonia molecule ligand. How do you think the sigma donor ability of ethylene diamine compares to ammonia? Do you see at a glance these are very similar molecules as with respect to the nitrogen functionality? Each nitrogen is sp3. This nitrogen has got this nitrogen associated with 2 nitrogen-hydrogen bonds. Here, 3 nitrogen-hydrogen bonds. The only difference is here you got one NH bond, where instead here you got one NC single bond. Okay? How does the electronegativity of hydrogen-carbon compare? They're close. Carbon's a little bit more electronegative. So do you accept my statement that these are, as donors go, very similar? Would you be surprised to find out that the Bronsted base strengths of these are very close? How might you verify that? How about looking in the acid-base table, where you'll see these molecules listed with their Kb values. Ethylene diamine Kb is about 8 times 10 to minus 5. Ammonia Kb 1.8 times 10 to minus 5. So ethylene diamine is about 4 times stronger Bronsted base. Now then, back to liganding. Water. How do you think the sigma donor ability of water compares to the sigma donor ability of ammonia as well as ethylene diamine? Well, when these things bond with H+, we know that this makes the strongest bond. Well, what about bonding with a metal? On what basis could we expect in bonding with a metal like cobalt in the +2 oxidation state that this would still make a stronger bond than either of these? What has a metal got after coordination takes place that H+ doesn't have? It's got valence d electrons. Because what's particularly interesting about this aspect of bond formation is that when a ligand does its liganding thing, after you make a coordinate covalent sigma bond with the metal, you have to pay attention to whether or not the donor atom of the ligand still has any remaining non-bonding electron pairs. There's another ligand, a particularly good ligand, but a lousy Lewis base. This thing doesn't attract H+ worth a damn, but this thing interacts quite strongly with a whole lot of metals. On what basis might we be able to rationalize that? You recognize, by looking at the Lewis pictures, are you surprised, that after this thing bonds, using this non-bonding pair, there's no residual electron density on the donor atom. After this thing bonds, there's still one residual non-bonding pair. After this thing bonds, there's 1, 2, 3 residual non-bonding pairs. And these non-bonding pairs, which remain on the donor atom, affect the bond strength positively or negatively. Negatively, because they constitute electron repulsion with the d-electrons, valence d-electrons of the coordinated metal. Interesting. Which allows us to realize why this, for example, as a ligand, is oftentimes found to be much stronger than this and this, and even this on occasion. Because this thing, beside making a sigma bond, can do what else? Make pi bond. But those can't. Oh, this can. This can, but that can't, and that can't. Interesting. So, with that, we go back to the question of what might we expect to happen if we treat this stuff, which has got 2 ammonia ligands and 2 water ligands and 2 chloride ion ligands with ethylene diamine. We would observe that that thing would convert like a shot to this thing. Or all these ligands are kicked out of coordination and replaced by ethylene diamine. Where all monodentate ligands are replaced by bidentate ethylene diamine. And then we write the reaction equation. And when you write the reaction equation, at a glance you can see this reaction is driven by a very, very large favorable change in entropy. Most of you looked at this yesterday. It's called the chelate effect. It's associated with the entropy change that takes place when you replace monodentate ligands with bidentate ligands, or any polydentate ligand, and make chelates. Because you're taking, in this case, 1, 2, 3, 4 moles of reactants, converting to 2, 4, 6, 7 moles of products. Delta S says, yay! I like this. Now, what's the other part of determining thermodynamic favorability? This part. Do you think this might also be associated with a significantly exothermic change in enthalpy? The answer is you betcha. Why is that? Well, they're not getting much of a change in enthalpy boost from replacing ammonia with ethylene diamine, because as far as donor strengths are concerned, they're very near the same. But what about replacing water molecules? That's bond improvement, because ethylene diamine is a much better donor than water molecule. What about replacing chloride ions? More bond improvement, because ethylene diamine molecules are much better sigma donors than chloride ions. So not only is this thing driven by a big favorable change in entropy, it's also driven by a large exo change in delta H. Interesting, isn't it? Now what about the complex we got? Here's the model. It's a little bit more compact than these. I don't have enough parts to make these, to use those parts to make this thing. This is a chelate ring. Here's the complex cobalt. How many atomic members in this ring? 5. 1. Imagine a nitrogen here. Imagine a nitrogen here. Imagine a carbon here. Imagine a carbon here. So this is CH2, CH2, NH2, NH2. I purposely leave out all these peripheral atoms because this would be a mess. So I just show you the loop. 1 chelate ring, ethylene diamine chelate ring. Another, and the remaining ethylene diamine chelate ring. So here is a geometric isomer for this complex cobalt with 3 ethylene diamine chelate rings. Never mind the difference in colors. Does this look like the mirror image? Here's the rings, here's the mirror. The top loop is oriented in space toward you. The bottom loops are each oriented in space toward me. Are these different or the same? Let's try the superimposition test. We'll overlay these loops, and now we see that we've got the bottom loops being projected in different spatial orientation directions. Same with the top loops. So this thing too is optically active. What might I do to turn this into this? Break and remake 2 bonds. That's all there is to it. Keeping in mind that ethylene diamine or any of these chelating ligands can span, connect cis coordination positions, not trans coordination positions. When we make a chelate ring, we can go from here to here, and then from here to here, and then from here to here. But you can't go from here to here in one fell swoop. You see why? If we have an octahedral complex, and we imagine the chelate ring to connect this coordination position with this coordination position with one large ring. That ring has got material composition. And the material components of that ring are bound to interact with these equatorially oriented ligands. That would lead to steric block, steric hindrance. It's like trying to put 300 students in the same phone booth. You can't do it. But you can connect here and here because then you don't have any steric hindrance. So keep in mind, if you're going to consider formation of any chelate rings, you can only connect cis coordination positions with each ring that you form. If you've got a tridentate ligand, you can go from here to here to here, here to here to here, here to here to here. But you can't go from here to here in one fell swoop.
How do you know if it's like a bidentate or a tridentate?
You'll be told. For example, let's go to the laboratory, take ethylene diamine, which is this, and do some chemistry on it and convert it into this. Let's do some more chemistry on it and convert it into this. Now it's tetradentate. Let's do some more chemistry on it and make it pentadentate. And more chemistry, I can make it hexadentate. And there are molecules like this. Have you ever heard of ethylene diamine tetraacetic acid? Shorthand reference EDTA? Have you heard of EDTA? That's an interesting ligand because it is a single ligand which can make an octahedral complex all by itself because it's got 6 donor atoms. It has a geometry similar to this. It's not exactly the same as this, but it is a consequence of reacting ethylene diamine with acetic acid. And that's where you get this name, ethylene diamine tetraacetate anion. Interesting. You can look it up and find out about it. Now, one more thing on this, since we got the picture here, is how can I recognize on my piece of paper that these are different? Play the same game as we did before. Model. Hold the model top and bottom, and rotate 180 degrees, which would mean if the ring is this way, you're going to turn it until the ring is this way. So I'm going to take this, rotate it 180 degrees. So this ring is going to come over here and be simultaneous with this ring. Now then, these atoms are still in the same position. But you see that where this ring connects? When I did this 180 degree rotation, where's this connection location going to be? It's going to be here. Just like this connection connection location rotated to here. Same as this? Not at all. And that's the way you can play the game. All right.